A quick Chapter 6 review. What do you need to know from 6.1? You need to know about rectangular approximation. These are called Riemann sums, and there are three ways to do it. You can do a left endpoint rectangle, in which case your value will be slightly less than the original for an increasing function. You can do a midpoint rectangle, in which case your value will be relatively close. And you can do a right rectangular approximation, in which case for an increasing function your value will be above. So again, notice that you lose a little bit here, you gain a little bit here, and these sort of maybe balance each other out a little bit. What else do you need to know about rectangular approximations? Why do we do them? We're talking about the area under a graph. And remember that the area under a graph is an accumulation. So if you have a graph of velocity times time, the area under that graph, well, each of these rectangles is velocity times time, which is distance traveled. All right. If you're using data, if you're given a data table of XY values, then what you typically would do is average each pair to find the midpoint of that rectangle. Riemann sums, you also probably have a program in your calculator, especially if you are in my class, which allows you to calculate these Riemann sums. It'll let you choose how many rectangles and allows you to get a slightly more accurate approximation of the value. But for purposes of my class or any AP test, you should be able to take any function and split it into the designated number of rectangles. And it doesn't really matter. You should be able to do it for left, right, or middle, sorry, and calculate that area by splitting it into rectangles. Section 6.2, we started talking about the idea of an integral, and an integral is basically just that Riemann sum, but we use slightly different notation, and it is the limit as the width of that rectangle goes to 0. So we know that area is equal to the integral from A to B, left end right end of the function with respect to x. And that's generally not super important until we get into slightly more advanced, and then we can maybe start changing that and saying with respect to something else. So you do want to be a little bit careful with that. If we are looking at area, we are moving left to right, then this area will be positive, and this area will be negative. But understand, and this is going from A to B, the integral from A to B, if I reverse the process and I go from B to A, whoops, don't know why, there we go, B to A, the red area will then be positive, And the green area will then turn into negative because I am working my way from left to right. So I am subtracting that area instead of adding that area. So I'm adding area as I move to the right. I'm subtracting area because I am moving to the left. Okay, let's see. 6.3 properties of integrals. I'm not going to go over them here in the video. On page 293 of our calculus book, there's a list of properties of integrals. I also gave a handout. And if you're just here to learn a little bit more about calculus, then jump on the internet and type in properties of integrals, and you will find multiple resources. We will add one more thing, is that the average value of a function is the area under the curve from A to B. So you take that total area under the curve, and then you divide it by the width of the curve. And that is an important equation to know. Mean value theorem for definite integrals. So we have thing one, a continuous function on some interval, closed interval. Then there has to be some c such that the value of the function at c is equal to the average value of the function on the interval. So very similar to the mean value theorem. But again, now we're dealing with average values. In other words, you can't get somewhere on a function without going through the average value. If all the points on a function are above the average, well, then you're never actually, it's not going to be the average. Okay, section 6.4 in our book, what do you need to know? The fundamental theorem of calculus. There are two parts. The derivative of an integral from a to x is equal to the original function at x. That's the first part of the fundamental theorem. And then we can extend that by saying, what if I have some other function up here? And we just use the chain rule. This becomes f of g of x times the derivative of g of x. So that is 1/2 of the fundamental theorem of calculus. We'll define an antiderivative, and this will become useful in just a second, as being the integral from a to x of f of t dt. This is an antiderivative. And I'm going to erase that t and put an x in there, so please change your notes. And the other half of the fundamental theorem of calculus says that if I want to take the integral from a to b of the function, that I can find the antiderivative at b and then subtract the antiderivative at a, and that is the value of the integral. So that will become very useful moving on, because anytime we have a definite integral, in other words, a and b are numbers, we can actually calculate the value of the area under the curve without having to go to our calculator and do a big long Riemann sum, have it calculate that for us. And finally, the last thing that we talked about in 6.5 was just the idea of a trapezoidal sum. And it is exactly what it sounds like. We've got our function, and we calculate the area using trapezoids. And the nice thing is with a trapezoid, you can see that we lose very little area when we are doing trapezoidal sums. And there are some shortcuts with trapezoids, but the main thing to remember is that the area of a trapezoid is B1 plus B2, all divided by 2 times the height, which in this case is our delta x. And then, of course, the area underneath the whole thing is the sum of all the a's. Okay, that I believe covers everything that was in Chapter 6. Obviously, the important part is being able to use it to solve problems, and then also being able to think about how does that apply to various scenarios. And let's see, I think, yep, that's it. Thanks for watching. Hope you learned.